Hello everyone, welcome to Module 2. We're going to be discussing networking concepts. So let me just get the screen ready for you. And let's just start on Module 2. So I'm hoping that by now you have a good understanding of at least a general idea of what the cloud is, right? We talked about different definitions. We discussed several of the things people looking for, whoever the provider is, things like reliability, the availability, scalability, and we define those terms, and I hope by now you have an understanding of what that means. And that's going to be important when you start recognizing the different services and the different things that you can do in the cloud. You're going to be looking at those kind of factors in order to understand what the system is able to do and in order to make decisions going forward. We also discussed some of the major players in the cloud business, including Amazon, Microsoft, and Google. And we determined that Amazon is the largest of them all. Being the largest makes it a little bit complicated because they have a lot of services, and some of the things can be a little confusing, especially when you look at the way they divide costs and services. So, but it's just one in the overall picture. So it's just one minor, relatively minor issue with the cloud in AWS. So before we actually look into the different services, we need to have a good understanding of certain concepts, okay? Not so much because you need to, you need to study networking. It's not a networking class, but I want to give you enough information so that you understand when you start looking at the services, you have a good understanding of what those things may mean or what those things may do and affect the different decisions you're going to make. So, don't be too concerned if there are a lot of new topics here. It may not be new for a lot of you, but it may be new for some of you. But we're going to be mainly just using those concepts to have a general understanding of what they mean when we start looking at the different jargon used in the cloud. It's going to make more sense, hopefully. Okay. So in this module, we're going to study some basic concepts, like I said, related to computer networks. And these are just things needed to understand how services and applications can run in the cloud. So we're going to be looking at networking basics, what is called the OSI model. We'll explain what that is. How computer networks communicate. What are protocols and what they use for. Another model that is called the TCP/IP model, and the concept of IP addressing, and how that all relates again later for cloud services. So what is a computer network? Well, again, most of you have an idea what that is. Even if you haven't studied networks, you have that basic knowledge. But a computer network, and this is a definition for Wikipedia, by the way, is just a group of computers. They use a set of common communication protocols, and that's, again, that's the key word, protocols, right? We'll explain what that is. Over digital interconnections for the purpose of sharing resources located on or provided by the network nodes. The network nodes are just the end. A node can be a computer, it could be a printer, some sort of endpoint where the communication ends. It could also be a point where the communication starts. So that's the basic definition. So we're going to start by looking at what is called the Open Systems Interconnection, or OSI model. And it's a conceptual model that was created in order to enable the communication systems to communicate using standard protocols. Is a model that helps the different manufacturers of network communications, the different users of network equipment, to have a standard, so to have a way of agreeing on how they're going to communicate. So that's what the OSI model is. It provides a standard, like I said, and so that they can communicate among the different networking components. So the OSI model includes 7 layers, okay? And it starts from what's called the application layer down to the physical layer. The application layer is your computer, for example, is the end user interface into the model. It goes down to, like I said, the different layers, presentation, session, transport, network, data link, and physical. The physical layer is the other end, is the actual physical cable connection. It's the physical infrastructure, your fiber, your coax cable. It could be wireless also, is the end connection point. So, you know, when you communicate on the internet, for example, you start, you know, by going into an application. You're going into an application like a web browser, and that web browser uses, you see some of the different terms there, like HTTP. You may have heard HTTP. It's nothing more than a language that is used by web browsers to communicate. Okay? But the point here is that, as you can see, you start off at an application when you go and use a browser and start using these different systems that are really called protocols. HTTP is a protocol, okay? And what's important here is that when you start, you know, like doing a search in Google, go web to a browser, you are using the HTTP protocol. From there, when you start communicating, it goes into all those different layers, okay? Down to the physical layer, and where at that point is where the actual, your communication is being sent, all right? When your search is being sent through either a cable or wireless, okay? And so there are different layers before, you know, by the time you do that search to the time you send that search, the data that you're sending goes through different layers, and those are the layers that are represented here by this picture. But what's important, again, is not so much to understand what happens at every layer, because it's just a large topic that we don't need to go into, but to understand what the OSI model is and what it is used for. It's used for the communication from one end to another in between networks. And every one of those layers uses different protocols. A protocol is just a language, right? And we'll get into that in a little bit. Here's another picture of the OSI model, and it kind of shows you a more graphical way of seeing what happens at every one of those layers. For example, if you look at the physical layer, at the very bottom of the picture, you'll see that that's being used by different hardware components. If you look at the network layer, that the data or the information handled by that layer is used by other type of different hardware components. At that level, you use things like switches, routers, are the ones in charge of handling the communication. If you go all the way to the top and look at the applications, that's what I was telling you about before. You're actually using an application like email or Google, something like that. And it's just another way of looking at what happens at every one of those layers. Another picture of the same, this time, again, another representation indicating what kind of happens at each of those layers. And another division for the model, which divides some of the layers are specific to the operating system, and some of the other layers are specific to the network. So the network is responsible, for example, for handling what happens from the transport layer down to the physical layer. But the operating system is responsible for what happens at the application, the presentation, and the session layer. Okay. This is again another one, indicating some of the layers as they define as a software layer, and more like a hardware layer. And again, the hardware layers are more related to equipment that's being used physically as information is being sent or received. So because it goes both ways, right? If you look at this model from the point of view of a sender being new, for example, you're using an application, you are doing a search in Google, you are sending that to the internet, to the Google site. So you're being the sender. So you start the application layer, and your information is then encapsulated in all those layers: presentation, session, transport, and it goes down to the physical layer, which again is going to be your cable or your wireless, and it goes out to whoever the recipient is. Well, and then it works the other way, because when you do that search, you expect to get something back. So when you get that something back, you are receiving the information, right? And it happens so quickly, you don't even blink while all that is going on, but it is going on. And it takes, it takes time. It could be milliseconds, could be seconds, depending on how fast your computer, your communication, and your bandwidth and all those kind of things are. But it takes time, even though it is so fast that by the time you receive that search information, then it goes from the bottom up to the top to you again at the application layer. Okay, so in order to understand how data is being moved among the different layers, we need to understand a couple of terms. One of them is a frame, and one of them is a packet. Think of frames and packets like envelopes. When you send a letter out in the regular mail, snail mail, if you put a letter inside an envelope, well, that envelope contains the letter. The letter is your data, right? But you can also put another the same envelope into a larger envelope, right? And so the data is still there. Your letter is still inside those two envelopes. But one of them can be referred as a frame, and one of them can be referred as a packet. So in essence, that's what frame and packets are. It's just different ways of encapsulating the data. A frame can be defined as a data unit, and it's used at the data link layer. And that's the difference. Where is it being used? Okay, if it's at a data link layer, then that is called a frame. On the other hand, a packet is the protocol data unit used in the network layer. Okay. Frames are formed in data link layer of the OSI model, where packets are formed in the network layer. Framing includes the source and the destination, the MAC address. The MAC address, if you never heard of what that is, it's just the physical address of your machine. Every machine that is built has an address. It's not the same as your internet address. The MAC address is unique. It's unique to every computer. Every manufacturer that builds computers will get assigned a MAC address. Network cards have specific MAC addresses. It's just a number to identify your individual computer, your individual printer. Could be any other device that communicates in the network. In contrast, packeting includes the source and destination IP address. So, remember again, your data, as I mentioned before with like a snail mail example, your data is still inside an envelope. What you put outside that envelope is what makes the difference, right? Whether you use a zip code, a PO box, the data is going to get whatever it's going to get. And so in networking, it's sort of the same idea of using different ways to identify where the data is at any point in the routing and where it's going. And this is a more graphical way of looking at it. Hopefully you'll get the picture. We call the segment, think of it as segment where your data is, and then the packets are encapsulating that segment. And then the frame is what encapsulates those other two. So again, at the end of the day, the segment, your data is what's is being processed. But as it's being processed along the different layers, it's just given handled by different ways of accessing that same information. All right, so if we look at each of those layers, as we mentioned, layer 7 is the application layer. It supports end user processes like file transfers, email, web browsing, that kind of thing. Presentation, at the presentation layer, the information is translated back and forth between application and network formats. This translation transforms the information into data the application layer and network recognize regardless of encryption formatting. Again, remember, the first 3 layers is what is called the software layers. And then the other 4 are called the network layers. And it's just a way of those layers understanding what the other ones do in order to communicate. That's what is happening. The session layer is where connections between applications are made, managed, and terminated as needed to allow for data exchanges between applications at each end of the dialogue. And then the transport layer, which is layer 4, complete data transfers ensure as information is transferred between systems. The transport layer also assures that there's an appropriate flow control and end-to-end error recovery. So, as data move among the layers, there could be errors due to, different factors in communication. And so the transport layer is one of those places where errors could possibly be corrected. The network layer, using switching and routing technologies. This is a common, famous layer where the routing and the switching takes place. That's where you see the routers and the switches use it. And is responsible for creating visual circuits to transmit information from node to node. Other functions at this layer include routing, forwarding, addressing, and so forth. And the data link layer, information in data packets are encoded and decoded into bits within this layer. Errors from the physical layer flow control and frame synchronization are corrected here using transmission protocol knowledge and management. Again, you notice that it's just the same data is being treated differently at every layer, just in order to make sure, for one thing, that the data is going to get where it needs to get to, and that if there's errors along the way, those errors can be corrected. And then the final layer, well, from the sender point of view, I guess, layer 1, it's called the physical layer. This was the one that enables hardware to send and receive data over a carrier. It conveys the bit stream through the network at the electrical and mechanical level. And some of the protocols used here are the Ethernet, ATM protocols, sort of like the languages that are used at that level. So again, when you get down to the physical layer, the communication is taking place in terms of bits. All right, so this is the first exercise in the in this module. Again, by this time you know how this works. Make a note of your choice, and the answers are provided at the end. It's important that you take your time to do this. You can pause the video, take all the time you want, but it's important that you are keeping with the understanding of what's going on as we move forward, okay? Now this brings us to the concept of protocols. A protocol is just simply a set of rules or algorithms which define how two entities can communicate across the network. Think of it as a language, right? If you speak English, somebody else that speaks English will understand what you're saying. Well, it's the same, basically the same thing. The rules. At each point within the layers, there are different protocols. They use different languages to communicate. Examples of protocols, names that appear very often: TCP, DHCP, FTP, HTTP is one of those, and so forth. And you're going to see many of these names in the cloud environment. You're going to see them all, you know, in many different aspects of the services. And that's what's important here, that you at least, not so much that you have a real knowledge of how the protocol works, which is not our point, but that you have a reference, right? When they talk about a protocol, you understand what a protocol is and what it can maybe use along the way. An important protocol is the IP address protocol, okay? And it's also known as the logical address. It's the network address of the system across the network. It's different from what we defined before. Remember, before we talked briefly about a MAC address. A MAC address is the address of the physical device. That address is fixed. It's given to every network card, to every computer by the manufacturer, and is unique to that device. The IP address, however, is different, and we'll explain the differences here. To identify each device in the World Wide Web, this association called the Internet Assigned Numbers Authority assigns what is called IPv4. You're gonna hear that term very often in networking environment and in the cloud environment. IPv4. It just means the Internet Address Protocol version 4. That's what the current version. Well, there's another newer version, but this is the most widely used version. And assigns a unique an address as a unique identifier for each device on the internet. So this is the addresses that the internet uses to communicate. Any network uses those addresses to communicate among the devices. Important thing to remember here is the length of the IPv4 address is 32 bits. So that means that there are 2 to the 32 IP addresses available. That's a huge number, right? Another definition, a protocol is a set of defined rules which has to be followed by every connected device across a network to communicate and share information among them. Protocols facilitate end-to-end communications, and they can work together to form what is called a protocol suite or a stack of protocols. Again, some of the most famously used protocols are the IP, or the Internet Protocol, FTP, the File Transfer Protocol, SMTP, Simple Mail Transfer Protocol, and HTTP, Hypertext Transfer Protocol. HTTP, again, is what is used by web browsers. And every time you use email, without realizing, then you're using the SMTP protocol, transfer protocol. Your data is encapsulated using that protocol, and that's how it gets to the destination and so forth. Okay, so this brings us back to the point of understanding the term port. It's another term you're going to see very, very often in our course. And the port can be referred as a logical channel through which data can be sent or received to an application. Any host may have multiple applications running, and each of those applications is identified using the port number. So certain applications use a specific port number. Okay, you'll see how that is applied in a minute. A port number is a 16-bit integer. So there are 2 to the 16 ports available. For example, and this is the relationship here between protocol and port. The HTTP protocol uses a specific port, and it's called port 80. Okay, so whenever you see port 80, it really means HTTP is being used. And whenever you see HTTP, it means it's using port 80. Okay, that's just a convention. When you use SMTP, your email protocol, it uses exclusively port 25. So port 25 means that you're using SMTP. And by using SMTP as the protocol, the way of communicating, it means that it's using that specific port to communicate. All right? The next thing we're going to talk about is the DNS server. DNS stands for Domain Name System, and it's basically a server which translates web addresses or URLs, for example, google.com, into an IP address. Computers, network devices really don't understand google.com. They understand an address. Okay? We don't have to remember all the IP addresses of each and every website. Obviously, we don't, right? We just type the name, and the system responsible for translating that name into an IP address is called the DNS server, which uses that the domain name system. And again, it's just a way of translating a .com, .net, whatever name into an IP address. Okay. The next protocol is called the ARP, and it stands for Address Resolution Protocol. And that's the one that converts the IP address into a physical address, a MAC address. So the two addresses can then understand the IP address is mainly used again to get to the destination. But once it gets to the destination, the MAC address specifically pinpoints to the actual device. Okay. ARP, and this is the protocol that does the translation. Understand how to go from an IP address to a MAC address and vice versa. Okay. ARP is used by the data link layer to identify the MAC address of the receiver's machine. So the OSI model we just look at is really just a reference model. It was designed to describe the functions of the communication system by dividing the communications into all the different layers. But when we talk about the TCP/IP model, this is the one that is really currently being used by networks and by the internet. And it stands for Transport Control Protocol / IP Internet Protocol Model. And it was designed in the 60s and is based on the standard protocols. It has 4 layers, unlike the 7 layers of the OSI model. So it's like a subset of the OSI model, but that's what networks use, okay? It's very similar, but it doesn't divide the communications into 7 layers like the OSI model. The OSI model is more like the template, but the TCP/IP model is the one that's actually being used by by networks. So the TCP/IP model includes 4 layers. The application layer, which is the highest, is concerned with the data, like the URL, the type, where the HTTP, the protocol, comes in. The transport layer, which is responsible for end-to-end communications. The internet layer, which is responsible for transferring data between the source and the destination computers. And the network layer, which provides data routing. Okay. Again, this is all a little bit, maybe a little bit complicated, but we don't need to go into the details of how all of this works. But just to understand where these keywords may fall in place along the way. Okay. Another picture showing the difference between the OSI and the TCP/IP model. And again, the TCP/IP model is doing the same thing as the OSI model. It's just that combines layers so that it uses a 4-layer model instead of a 7-layer model. So in the TCP/IP model, the internet layer is similar to the functions of the network layer in the OSI model. It defines the protocols which are responsible for logical transmission of the data. And within this layer, we find some important protocols, which, as we mentioned before, the IP protocol is where the internet protocol is where this can be used in the internet layer. And like I said before, it stands for Internet Protocol. You're responsible for delivering packets from the source host to the destination host by looking at the IP address in the packet headers. Sort of like, remember when you send a letter and you may describe a zip code. Well, the letter or the mail, in this name mail, is gonna first define where it needs to go by looking at that zip code, right? And then once it gets into the zip code, it uses a specific street and number to get to the final destination. So IP has two versions. We briefly talked before about the IPv4 version, which has 2 to the 32 addresses available. And there's also a newer version called IPv6. IPv4 is the one that most of the websites are using currently. But IPv6 is growing because, as I mentioned before, IPv4 give you 2 to the 32 because this, remember, the size of IPv4, any address in IPv4 is 32 bits. So there are 2 to the 32 available addresses, but even the huge number is becoming too small, or it became too small because you know, when this protocols were first designed, you know, there were a lot of fewer systems that were considered computers at the time. You know, a computer was a more defined instance of what it was. You know, years ago, a computer was just a computer. Nowadays, any device is computerized, right? Your televisions, your phones, your refrigerator, your washing machines, you know, now may have IP addresses, right? They're devices, they're smart devices. And as a smart device, they use an IP address because now they become part of a network. So the demand for IP addresses went up, you know, huge increase. And so eventually it became a problem. The 2 to the 32, you know, addresses available became a small number. So they came up with a new protocol called IPv6, which makes the number of IP addresses available a larger number. Okay. So in the internet layer, another protocol we found is the ICMP, which stands for Internet Control Message Protocol. It is encapsulated within IP datagrams and is responsible for providing hosts with information about network problems. And again, this is where we find the ARP protocol we mentioned before. The ARP is Address Resolution Protocol. Its job is to find the hardware address of a host from a known IP address. And then the host-to-host transport layer is analogous to the transport layer of the OSI model and responsible for end-to-end communications and error-free delivery of data. It shields the upper layer applications from the complexities of data. The two main protocols present in the transport layer are the TCP protocol. It's known to provide reliable and error-free communications between systems, and the UDP protocol, a user datagram protocol, is what's called the go-to protocol if the application doesn't require reliable transport and it's very cost-effective. The difference is that TCP protocol is what is called a connection-oriented protocol, whether the UDP is connectionless, and we'll explain what that is later. And in the case of, basically what it means is that the TCP protocol sends something out. It expects a message back saying that the data was received, for example, in order to send the next packet. Well, UDP doesn't. UDP sends it, and whether you receive it or not, it doesn't care. But it's just, another way. Different systems communicate different ways, and it's just the two ways that a system can communicate. The process application layer performs the functions of the top 3 layers of the OSI model: application, presentation, and session layer. It is responsible for node-to-node communications and controls user interface applications. Some of the protocols in this layer, again, could be HTTP, HTTPS, and so forth. The network access layer corresponds to the combination of data link layer and physical layer of the OSI model. Remember, we saw that picture earlier where we see how the network layer combines some of the original OSI model layers. And I know that there may be a lot to absorb here, okay? But remember that one of the main goals is not so much that you understand every aspect of the networking protocols, but mainly that you're becoming familiar with the terms. When we found them later in discussing cloud services, okay? So don't get too bogged down if there's a lot of information here. It's also important that later you can then maybe even refer back to this lecture and say, okay, that's what I found, and let me review where I saw that before, okay? And so as we know, the World Wide Web is a subset of the internet, right? The web is not the internet. There's more to the internet than just the web. But the web is a system of internet servers that support specially formatted documents. The documents are formatted using the what's called the HTML language. This is also called a markup language. These documents are interlinked using hypertext links and are accessible via the internet. To link hypertext to the internet, we need the markup language. We need a transfer protocol, and we need a URL, or the address of the resource. And of course, we access the web using web browsers, okay? And then this brings us to the different network types. Mainly, they are categorized by size and functionality, and they can be categorized by name. LANs stands for local area network, MANs stands for metropolitan area networks, and WANs stand for wide area network. And again, it's just, the size of the network basically defines the name, right? A LAN is typically your company network. The MAN expands that, that idea into a larger environment like a city or a state. And then the WAN is just the, overreaching aspects of larger networks that maybe even go out to different regions in the world. But the main thing to also notice here is that not so much the size at this point that defines the different names, but what happens is that when you use LANs, you use certain devices that work within LANs. Certain protocols communicate within LANs. When you go into a MAN or a WAN, then there are devices that are built, hardware devices, to work with larger networks. And there's also different kind of protocols that are used to handle and to manage larger networks. Some networks are categorized by their function as opposed to their size, and an example of that is what is called a SAN, Storage Area Network. A SAN provides systems with high-speed, lossless access to high-capacity storage devices. There's also a VPN. VPN stands for Virtual Private Network. A VPN allows for information to be securely sent across a public or unsecure network, such as the internet. As you know, the internet is not a secure network by default. Once information goes out on the internet, it's really not that secure. But the different ways of securing the data while it's being transported, right, from source to destination and back to the source. But by default, the internet is not a secure way of communicating. But one way of making it secure is using what is called a VPN. And later we'll see a little more about VPNs. Common uses of VPN are to connect branch offices or remote users to a main office. Okay, and so you're still using the internet when you use a VPN, but that VPN is really more restricted within for your communications. In a network, any connected device is called a host. Remember we said that, right? It could be a printer, it could be an actual computer, anything. It's called a host. It could be your, it could become your refrigerator, right? You probably heard the term Internet of Things, where every device can be a smart device. So any of those devices could be a host. A host can act as a client when it's requesting information, but it can also act as a server when it's providing information. A host can also request and provide information, and when it does that, it's called a peer. We mentioned these protocols before, especially the HTTP, and so HTTP stands for Hypertext Transfer Protocol. And in the case of the HTTPS, it's just a version of HTTP used for secure communications. And you've seen that before when you connect to a secure site. You've probably seen that green icon next to the address, or you'll see a lock indicating that that's an HTTPS protocol being used. So an HTTPS is just a combination of two protocols, actually. The HTTP protocol and another protocol called Secure Socket Layer, SSL. And at the end, all it means is that with HTTP, you're using a secure site. It uses encryption. Later we'll see what encryption is, but encryption basically means you're securing your data so it doesn't, is not plainly visible to anyone. Okay, it is efficient in cases where the browser needs to fill out forms, like as you've probably seen it, authenticate, carry out bank transactions, and so forth. Okay, more protocols. Again, this will be for your reference, so you'll know, at least you'll know where to find them later if you need a definition. SSH stands for Secure Shell, is a protocol and software suite used for transmitting data securely. It sets up a secure session over a TCP/IP connection. And then the NTP network time protocol is used to synchronize the clocks of our computer to one standard time source. And it's very used in situations where you need to do things like bank transactions, so the timing is always synchronized. So let's go back again to an IP address, right? And because it's important, we said that an IP address is a unique numerical address of a device in a computer network, and it uses the Internet Protocol for communication. The IP address allows you to pinpoint a particular device from the billions of devices on the Internet. To send you a letter, someone needs your mailing address. In the same sense, one computer needs the IP address of another computer to communicate with it, or another device. An IP address consists of 4 numbers, and each of those numbers can contain 3 digits. The numbers are separated with a single dot, and these 4 numbers can range from 0 to 255. The reason for the numbers, it comes from the remember 2 to the 32-bit, the 32-bit length of the IP. We'll see that in a minute. An IP address is a unique address that identifies a device on the network or the internet. It allows a system to be recognized by other systems. We mentioned there are two primary types, IPv4, IPv6. IPv4 is 32 bits, giving you address space of 2 to the 32. There are basically two ways of describing an IP address, two types of notation. One is called the dotted decimal notation, and the other one is called the hexadecimal notation. And this is an example of that. An example of an IPv4 address with a binary notation and with the hexadecimal notation. Of course, you all engineers, you hopefully know what that means or how you go from one to the other. I don't know if you're taking digital yet, but the two numbers, whether they're binary or hex, mean the same thing, right? If you look at the first set of numbers, the first binary numbers here, the 1 followed by 7 zeros, right? This is a binary number that represents a decimal of 128. Well, and the reason for that is because of the location, right, of the exponent. This first digit to the right indicates a 2 to the 0, 2 to the 1, as you move over to the left, 2 to the 2, up to 2 to the 7, right? So since these are all zeros, they don't contribute anything to the total number. The only one that contributes something will be this 1. So this will be position 2 to the 7 times 1. Well, 2 to the 7 times 1 is 128, right? And you probably know that already, but just so you understand. But the main point here is that these two numbers, these two sets of numbers, this set and this set, represent an IP address, IPv4 address, because you have a total of 32 bits, as you can see. And the 32 bits are divided into 4 groups, right? Each one is a byte long, right? 8 bits. 1 byte, 1 byte, 1 byte, 1 byte. That's 4 bytes. 4 times 8 is 32. Okay? And you'll see that often. And most likely you're gonna see hexadecimal representation of IP addresses because it's a lot easier to write for one thing, right? Another example of IP address in binary and hex form, right? Same idea here. This represents 75, this represents 95, and this will represent this IP address, all right? So there's a way of classifying addresses in using IP notation. One of the ways of classifying addresses is called the classful addressing model. And what it does is the 32-bit IP address is divided into 5 subclasses. And the names given are simple, class A through class E. Each of the classes is given a value range of IP addresses. Classes D and E are reserved for the things. We'll talk about that later, but some of those are reserved for experimental purposes. They're not used commercially. And one way of determining what class an address can belong to is because the order of the bits in the first octet determine the classes of the IP address. In IPv4, addresses are divided into 2 parts, a network ID and a host ID. Think of the network ID as a zip code, right? Again, if somebody snail mails a letter and places a zip code on the envelope, well, that's sort of the network ID, because by writing the zip code, it identifies an area. And so once the area is identified, then you will look at the street address. Well, think of the street address as the host IP. So your computer will be the final destination, okay? The class of IP address is used to determine the bits used for the network ID and the host IP, and the number of total networks and hosts possible in that particular class. Each ISP, or Internet Service Provider, assigns IP addresses to each device that is connected to the network. So depending on what class you use, as you can see in this figure, for Class A type of addresses, the first byte, the first octet, whatever you want to call it, the first 8 bits are used for the network, to identify networks, okay? And the rest of the bytes, looking at Class A, the next 3 bytes are used to identify or assign to hosts. And next class, if you look at Class B, is divided half and half. 2 bytes are assigned for networks, and the next 2 bytes are assigned for hosts. And what this simply means is that, again, this is the old way of classifying IP addresses. For example, if you look at Class A again, you have 2 to the 8 addresses reserved for the network, sort of having 256 zip codes, or 256 area codes, if you will, okay? And the rest, which is 24 bits, 24 because you already used this 8, right? And the total is 32. So the rest, the 24 bits, give you 2 to the 24, and that number is used for the individual addresses assigned to devices, or the individual phones, if you will, within that network, the whole neighborhood. Okay, I hope that makes sense. If you look at Class B has, again, if you think of the analogy of zip codes or area codes, in Class B, you'll have 2 to the 16 different zip codes, or 2 to the 16 different area codes, but you also have 2 to the 16 individual hosts, okay? For Class C is the opposite of Class A, all right? Most of the bits, in this case 3 bytes, are assigned for networks, and then 1 byte is assigned for hosts. So what that means, among other things, is that in the Class C way of using the addresses, you don't have as much addresses assigned to hosts, okay? This Class A will give you the most number of hosts. And how they use and why, we'll get into that a little later. Class D is used for what is called multicast address. Multicast addresses are used by devices themselves to do certain things within the network. They're not used by hosts or anything. They're used for internal communications, if you will. And then Class C, as we mentioned previously, is reserved. It's usually used for experimenting. So IP addresses, we mentioned, are globally managed by the Internet Assigned Numbers Authority and another entity called the Regional Internet Registries. They are responsible for assigning addresses to a company or to a governmental agency or whoever, an ISP. Okay. While finding the total number of host IP addresses, 2 IP addresses always, and this is a rule, when you look at the 32 bits, when you look at Class A, for example, when we saw that there's 2 to the 8 addresses assigned to the network, every time you see at that group of addresses, there are 2 particular addresses that are not counted, and so they're sort of reserved. The first IP address of any network is the network number. It identifies that individual network. And the last IP address is reserved for broadcast IP. Broadcasting is, again, another way of devices used to communicate. So out of the whole number that you see, whether it's class A, B, or C, there's always 2 IP addresses that are reserved. One specifically for the network, which is the first IP address. So that'll be address 00, 8 zeros. And the last IP address, which will be all ones, is reserved for what's called broadcasting. So let's look at Class A. Class A, IP address belonging to Class A are assigned to the network that contains a large number of hosts. We saw that already, right? The network ID is 8 bits long, and the host ID is 24 bits long. The high order of the bits octet in Class A is always set to 0. The remaining 7 bits in the first octet are used to determine the network ID. That's another rule. That first bit is always 0. We'll see some examples of that in just a minute. For example, remember, since there are 2 addresses that cannot be used, right? One's for the network and the other one is for the multicast. You really have a total of 2 to the 7th minus those 2 that we mentioned are reserved. So you have a total of 126 network IDs, right? Because we subtracted the 000, which are special addresses. And so when you look at the number of hosts, the same thing, you'll have 2 to the 24 minus 2 total host addresses available. So IP addresses belonging to Class A will always have a range from 1.xxxx up to 126.xxxx. So remember, when you look at this addressing way of dividing IPs, the first bit is always assigned as 0. So what you have is you have 7 bits available after that, and then the rest of it is the host. This is for Class A. Class B, we saw that already. It uses 16 bits for the network. It uses 16 bits for the host. The rule for Class B addresses is that the first 2 bits of a Class B address are always set to 10. So then you have 14 bits that are really used to determine the network ID. And we'll see this next. So in a Class B, you have, again, 2 to the 14 possibly network addresses, and 2 to the 16 minus 2, those 2 that are always used for host addresses. So for a Class B, you're always going to see this first 2 bits are set to 10. You can't change that. It's already given. So that gives you 14 bits available for your network address and 16 bits available for your host addresses. So that means that anything that starts with 128, that 0xx indicates a B type, a Class B type address. The 128, obviously, because if you look at this 1 here in the front, and if the first address, the all zeros, right, up to the last bit here, so this will be followed, the 1, the 0, followed by 14 other zeros. Then when you look at the first octet, right, you'll have 2 to the 7th, which will give you that 128. Class C, we said that before, the network ID is 24 bits long, the host ID is 8 bits long. In this way of classifying addresses, in a Class C address, the first 3 bits are always 110. So that's the rule. And again, same idea, right? So anything that starts with a 192-000 indicates that this belongs to a Class C type of address, right? Because in a Class C type of address, the first 3 bits are always 110. Excuse me. In Class D, which again is not really used by the nodes. But in essence, any type of a class D address, the first 4 bits are always assigned 1110. Okay? So anything that starts with a 1110 means that it belongs to a class D type address. Class E, just to identify, it always starts, the first 4 bits are assigned 1111. And this is the summary of that. So for the first byte, that's how you can identify what type of class the networking is using by looking at that first byte. If the first byte is between 1 and 127, you know that it belongs to a class A address. If it's between 128, 121, it belongs to a class B, and so forth. So a class A network contains 2 to the 24 hosts. A class B contains 2 to the 16 hosts, and a class C contains 2 to the 8 hosts. Remember, the hosts are the individual devices, right? For example, in this case, the 2 to the 8 host means that you're able to talk to 256 devices in that network, right? And here's your next exercise, okay? If you want to pause it, take your time, answer the question. Email me if you have any questions on this. The answers are at the end of the module. Another one, okay? What type of network is this? Well, if you look at the first number here, it'll give you that clue based on the figure we just looked at, right? Just to identify it. All right, so what we just look at is, again, what is called classful addressing. But it has become inadequate. We mentioned before that it's just not only that you can be really not used properly, because you ended up wasting addresses. There's no way of, as it was at the time when it was developed, there wasn't any way to divide those addresses. You know, if you're given a next number of addresses, that's all you had. So if you needed more, you were stuck with it. If you needed less, you know, maybe even worse. So classful networking was replaced with another method called classless. And specifically the name is classless internet domain routing back in 1993. We don't use the name classless internet domain routing. We simply call it CIDR. Okay, so you'll see this. You see this name very, very often. For example, and we mentioned that one of the reasons that they decided to move from a classful A, B, C, D, E type of address to the classless internet domain routing form is because addresses were being wasted. For example, think, let's say you have a medium-sized company with 500 computers or hosts, you know, not just computer. You need 500 addresses. You could have printers, computers, all the devices that are using addresses. But your company needs 500 addresses, 500 hosts, right? Well, if you use a Class C address, right, it wouldn't be enough. Because remember, with a Class C address, you can only have 256 hosts, but you need 500. Well, so what if you use a Class B address? Well, if you use a Class B address, this will be more than enough, right? Because with a Class C address, with a Class B address, you will have 2 to the 16 addresses available for your host. That means you'll have 65,534 IP addresses available, but you only need 500. So if you only need 500, you'd be wasting over 65,000 addresses, right? They're not being used. In the meantime, whenever you assign those addresses, those are reserved for your company. Those are reserved for your use. And by the way, you're paying for that through those services that that provide IP addresses. You pay for those addresses, but at the same time, you're paying for something that you might not be using. And so that's what also added to the problem of running out of addresses, because not only the number of devices just extrapolated so much to the point that everything needs an IP address, but also because of the fact that using this classful addressing, a lot of companies, a lot of entities were just not using those addresses. They were just, they had no choice, like in this example I just gave you, right? So that's the idea behind looking at something else. What can we use so that we don't waste those addresses? And this CIDR system is what resolves that problem. So again, a network, to understand how this works, we need to go back and look again at a concept of the network address. Again, remember, the network address identifies a network on the internet, right? So again, like a zip code, right? A network address may identify a company, for example, because it's assigned to that company. A mask is a term that is very commonly used in networking. Is a 32-bit binary number that is able to give you the network address when you use the AND operation. And you'll see how that is done briefly. It's not difficult. But with each of the classes, there are specific masks that are assigned to those classes, right? So class A, the default mask is always 255.000. For class B, it's always 255.255.00. And for class C, it's always 255.255.255.0. Now, if you remember from binary, 255 means that in each of those bytes, the bits are all ones, right? 255 is the equivalent of all ones in that specific byte. Well, you'll see that, again, this is fixed. This type of IP is given to each of the classes to identify the mask, and I'll give you an example. Let's say you have an address, right? You're given this address 132.6.17.85 in the default class B mask, and you want to find the beginning address. So in other words, this is the address of a device, right? Let's say it's your computer is given that address. But you want to find out what the network address is, okay? What will be the network address associated with this specific IP? Well, to find that out, you use the mask, okay? So the mask is the, since they're telling you it's a class B, you know that the mask is going to be 255.255.0.0, which means that only the first 2 bytes are preserved, and the other 2 bytes are going to be set to 0, right? Because if you AND, if you use the logical AND of this address here, right? If you AND this with this other number, remember, all these 255s are ones, right? If you AND something with a 1, it's gonna remain the same number. So we ANDing, 132 ANDed with 255 gives you 132. 6 ANDed with 255 gives you 6. And then anything ANDed with 0 will give you 0, right? So it's just a simple operation. By ANDing this IP address with the specific mask assigned to a class B, you get the network address. All right? It's that simple. So with classes addressing, it introduced a concept that is called subnetting. The process, subnetting, is nothing more than dividing a large block of addresses into contiguous sub-blocks and assigning these sub-blocks to different small-end networks. So it's sort of making a larger network into smaller networks. That's what subnetting is. is widely used in the classless addressing mode. And again, remember, classless addressing it became very popular because it reduces the waste of IP addresses. The networks are split into groups of IP addresses called CIDRs, or CIDR blocks. Use host ID bits as network ID bits of a classful IP address. And it uses a certain format to understand how it's being used. The IP address that is used is define the number of bits for mask along with the symbol. It usually is followed by a slash. So citing notation is really a compact representation of an IP address and is the associated routing prefix. The notation is constructed from an IP address, a slash or forward slash character, and a decimal number. And you see an example right here, 192-168 dash, I'm sorry, not dash, 192.168 .1.1/28. Well, we'll explain what that means in terms of CIDR notation. The number after the slash, in this case 28, represents the number of consecutive ones in the subnet mask. Right? Even if you don't understand what that means right now, just keep that in mind. So the number 28 means the number of consecutive ones in the subnet mask. In other words, the number subtracted from it represents the number of hosts. So since we have a 32-bit address system, 32 minus 28 gives you 4. So that means that this number is representing a set of addresses with 2 to the 4 hosts available. Okay. So let's look at this in more detail in the next slide. Okay, the actual notation. So you see this number here, right? 192.168.1.1. That's the IP address, and it's I know it's an IPv4 address because it's using 32 bits, and it has that /28, right? So the /28 is the number of 1 bits that are included in the mask, and you see that next, right? There are 28 ones for the mask. The mask is what's going to help me find the actual addresses, okay? So in the next 4 bits, you know, there are don't cares, if you will. We don't, you know, those are available to be used. So there are 28 ones, and out of the 32 total bits, then 4 bits are allocated for host addresses. So those 4 X's indicates that there are 2 to the 4 or 16 addresses available for the hosts. It's an exercise here. It says list the first and the last address that will be allocated to the host given the following CIDR. Remember, this is /28 is the same number that we used in the previous example. That means that you have 2 to the 4 possible addresses, 16 addresses available to the host. So what would you think the first address for the host is going to be? Right? Well, there's only 16, so but I'll give you some time to digest that. The answer again is at the end. And if you have any questions, I'll be happy to answer that for you. Just email me. All right, the next thing we're going to talk about is called DHCP. DHCP is used in order to manage the allocation of IP addresses. It's another protocol. It stands for Dynamic Host Configuration Protocol. It's a management protocol used on networks whereby there's what is called a DHCP server that is used to dynamically allocate IP addresses and other configurations, okay, so that it doesn't have to be manually done. But by using this type of protocol, you know, addresses can be also reused, right? They can be assigned and then reused later if somebody's not using it. Okay, it's a way of managing the humongous amount of addresses that could be available. DNS is another protocol that's important. We mentioned this one briefly before. Is a way of identifying a specific .com, .net, .org name to an IP address. Web browsers interact through Internet Protocol addresses. DNS translates domain names to IP addresses so browsers can load Internet resources. And this is exercise 5. And so this brings us to the type of IP addresses that you're gonna hear about, especially when you look into the cloud services. There are 4 types of IP addresses. Dynamic. A dynamic IP address changes frequently. Static address doesn't change. Public address, IP addresses are used for accessing the internet, and private addresses are used for accessing networks internally. And so later we'll see that there's a way of classifying these addresses and how they're used for and under what circumstances, but they're pretty self-explanatory, especially with the public address. There are certain ranges of addresses given to companies, and those addresses can only be used to communicate through the internet. And the other range of addresses that are given that can only be used to communicate inside a network. Okay, another difference between what a dynamic IP address is as opposed to a static IP address. They have different uses for different reasons. We'll see that later. The dynamic IP address changes frequently. Could be 24 hours, could be every week, every month, it doesn't matter. But it changes. A static IP address doesn't change. Static IP addresses are not efficient because you don't want to have something that it cannot be reused, but they're important because certain devices may require the IP to never change. Certain applications require you to have addresses that never change, and we'll see that later. One more exercise. Well, these are the answers to the exercises, so hopefully you got to this point. One thing I want to add that I think I didn't make clear when we talked about IPv4 and IPv6, because you'll see also the term IPv6 every so often when you look into computer cloud services. And this is the end of the module, by the way. But I just want to make the point that IPv4 uses 32 bits. So that means that you have the range of 2 to the 32 possible IP addresses. With IPv6, which is being used but is not as popular still, IPv6 gives you 128 bits available. So that means that the range of addresses available is 2 to the 128, and you can figure what that number is. It's very, very large. And so there are challenges associated with using that large number for certain applications, certain devices, and so forth. That's why it's not so popular, but it is becoming popular. The idea is still the same of how it's being used. It is not being used as a class-full system anymore. It's being used as a CIDR system, IPv4 or IPv6, where it can be used more efficiently. But it's just that the number of bits is a lot larger than with the IPv4. So when you see IPv6 later in some of the literature, that's all it means, okay? That the number of bits have been expanded from 32 in IPv4 to 128 bits in IPv6. So thank you, and I hope that that was helpful. And if you have any questions, please don't hesitate to email me.